Okay, here we go with matrix multiplication. So remember it, maybe you don't remember, maybe you didn't listen to it, but at the end of the last video, I said something about how matrix multiplication was hard. It is, at least it's harder than addition and scalar multiplication. All right, so I just copied this out of the book. This is the formula for matrix multiplication, and as you can see, it's a nightmare. It's got this like double summation thing going on, and just a huge mess. But once you kind of get the rhythm of it, it's not too bad. So I'm actually going to just get rid of this because it's unpleasant. So there's a couple of things to know starting out. Okay, so you can't just multiply any two old matrices. There are a few rules. So rule number one, the number of rows in the second matrix is going to have to be equal to the number of columns in the first matrix. Let me say that frontwards this time. The number of columns in X must be equal to the number of rows in Y in order for X times Y to exist. I said there were a couple of rules, but that's really not true. This is the only one. All right, so for example, if I look at the dimensions of these two things, here's a 2 by 3 matrix and another 2 by 3 matrix. They're the same size, so I could add them together, but the number of columns in this matrix is not the same as the number of rows in that matrix, so I can't find their product. A times B does not exist. DNE is for does not exist. C times D, though, that would exist because the number of columns in the first matrix is equal to the number of rows in the second matrix. So we would be able to compute that product. And in general, if you think about X, say X has dimensions n by m, and Y has dimensions a by b, then X times Y exists. Let me draw this as sort of a diagram. So here we have an n by m matrix, and this one has dimensions a by b. So these two have to match. You can kind of think of them as sort of canceling each other out. And what's left is n and b. And those two values, n and b, they're going to describe the size of the product matrix. All right, so let's do some practice. Okay, so there we go. Now we can play around with these a little bit more. So we already said that a times b doesn't exist. And then, of course, if we look at b times a, is that going to exist? Well, no, right? Because b times a would be 2 by 3 times 2 by 3. And those don't match, right? Those inner dimensions in this diagram have to be equal. And a times c, that would be a 2 by 3 times, let's see, c is a 2 by 2. And again, these are not equal, so that product doesn't exist. C times A, though, that does exist, right? So check it out. C is a 2 by 2 matrix, and A is a 2 by 3 matrix, and these do match, right? So that means that the product matrix will be those leftover numbers, right? 2 and 3. The product matrix of C and A will be a 2 by 3. So that's sort of interesting. I mean, for one thing, A times C doesn't exist, but C times A does exist. So you see right there that matrix multiplication is not commutative. And that's weird because regular multiplication is commutative, right? Like 3 times 2 is equal to 2 times 3. 15 times 79 is equal to 79 times 15. But that commutative property that's true of numbers is not true of matrices. Okay, so let's compute C times A. So C is this guy, 1, 2, 2, 0. And A is 2, 1, 3, minus 4, 1, 6. Now I know from my analysis over here that the resultant matrix is going to be, right, the matching one's going to cancel out. What's left over is 2 by 3. So I'm going to set this up as kind of a fill in the blank problem. So I have a 2 by 3 matrix to fill in. 2 rows, 3 columns. Every one of those little blanks has to get a number in it. And let me show you how this works. All right, so let's start with the 1, 1 entry. All right, so that 1, 1 means first row and first column. To get the 1, 1 entry of the product matrix, I'm going to use the first row of that matrix and the first column of this matrix. Think of those things as vectors and compute the dot product. All right, so I'll do 1 times 2 plus 2 times negative 4. That is negative 6. And so that's what goes in here. All right, how about another one? This one is in the first row and the second column. So I'll use the first row and the second column to get that entry. So it's always rows and then columns, right? So we use rows from the first matrix, columns from the second one. And now if I think of these two things as vectors, just take their dot product. Let's see, I'll get 1 times 1 plus 2 times 1. That's 3. So that's what goes in there. For this entry, I'm in the first row again, but I'm in the third column. So I'll take the third column, and I'm going to just pretend those two things are vectors and compute their dot product. Right? So this will be 1 times 3 plus 2 times 6. So that's 12, 15. And this same process works on the kind of going across down here in the second row, except now I'm in the second row. So I'm going to use the second row. The second row, first column. So I'll use second row, first column, and then take the dot product. So that'll be 2 times 2 plus 0 times 4. So that'll be 4. And for this 2, 2 entry, that's second row and second column. That's going to be 2 times 1 plus 0 times 1. So that's just 2. And let's see. Oh, colors. How about you? For this last one, I'm in the second row, third column. So I have 2 times 3 plus 0 times 6. 2 times 3 is 6. And so that's the product, C times A. So I hope you can follow that process. Let's see. Maybe we should do just one more example. And then it's really all about practice. Really, I can't say that enough. It's all about practice. There are a ton of matrix product calculators on the internet. Just make up some matrices and start practice calculating them. Let's see. So we did C times A. C times B also exists. And C times C exists, C times D. So let's do some of these other ones. How about we do D times C. All right, so D is minus 1, 1, 1, 1. And C is 1, 2, 2, 0. Right, this is 2 by 2. This is 2 by 2. So the resulting matrix, these guys kind of cancel out and they match, so we can do this. The resulting matrix is 2 by 2. So I have 4 blanks to fill in. 2 rows, 2 columns. And to get the 1, 1 entry, again, I'm going to use the first row, first column, compute a dot product. So minus 1 times 1 plus 1 times 2. So that's minus 1 plus 2. That's 1. And then to get the, say, the 2, 1 entry, I would use the second row, first column. So 1 times 1 plus 1 times 2, that's 3. And now to get the, say, this one, the 1, 2 entry, that's first row, second column, that's minus 2 plus 0, so just minus 2. Finally, to get the second row, second column, I'll do 1 times 2 plus 1 times 0, so that's just 2. Okay, go ahead, practice, practice.